We spent last week beginning our study of what we can say, if anything, about the cosmos as a whole, the universe in its totality. And before we move on to this week's material, I wanted to pause and emphasize that in my humble opinion, we know a whole lot, much more than one might have expected, in particular, assuming, as observations suggest, that the universe is both homogeneous and isotropic. The equations of general relativity simplify to essentially these two Friedmann equations that we wrote down. All of the history of the universe is determined by this one function of time called the scale factor, which determines how distances between otherwise stationary or co-moving objects grow. And the behavior of the scale factor is written down in these two equations, where you recall that h of t, the Hubble constant, which I agree, perhaps misleadingly, is not a constant. It is a time-dependent quantity, but at any time, it is the constant of proportionality relating distance to redshift at small distances and redshifts. And so this is related to that function by being the rate of change divided by the scale factor, or the fractional rate of change of the scale factor. And in terms of this, we can write our two Friedmann equations. Here's the analog of the energy equation, telling us that the square of the Hubble constant is determined by the total density of both dust and radiation in the universe, the contribution of the space curvature, the curvature of space here, and the cosmological term, which, as you recall, we will often rescale and stick in there as rewriting this term as 8 pi g over 3 rho lambda, and attributing the cosmological term to some dark energy type thing. This is one Friedmann equation. The second Friedmann equation is the acceleration equation down here. Remember that the time, this is essentially, this expression on the left-hand side is essentially the second derivative, the rate of change of the rate of change of A divided by A. So it's therefore called the acceleration equation. And this is determined by both the density and the pressure. You will recall that for dust, for the dark matter, cold dark matter particles, the WIMPs, and for galaxies and baryons, the pressure is essentially zero. For photons, these two terms are equal, and so for radiation, we get a factor of 2 here. And then the sign here in front of the dark energy term shows us that if we describe it by a density and a pressure, then it exhibits a negative pressure. And so solving these equations gives us the history of the universe, introducing the parameters that I claimed we have measured for our universe. This is essentially the answer. We see here our universe, starting at the present at the scale factor of 1 by convention at 13.8 billion years of age. We see that about 5 billion years ago, we made a transition from a dust-dominated universe where A grew like the 2/3 power of time, and we're making the transition to exponential growth with up to roots of 3, something like that. And hiding in here, too small to see in this figure, is a radiation-dominated era where A grew like the square root of t, and the parameters, the times at which all these transitions happened, are determined by some measurements of current parameters. But up to measuring these current parameters, we have determined the future, the past of the universe. There are some interesting questions that we will delve into this week, but I wanted to show you that, in fact, we seem to have much more than one would have imagined under pretty good control. I want to point out that the second Friedmann equation, the acceleration equation, we parameterize the right-hand side typically as minus qh squared. So absent a cosmological constant, q is this whole thing rescaled by h squared, so it gets rewritten in terms of the critical quantities. And the sign indicates the fact that, again, absent the cosmological term, all of these quantities are negative, and q has a name. It's called the deceleration parameter. It parameterizes in a sort of dimensionless way how much the expansion of the universe is decelerating. And so we need to measure some parameters. What is it that we need to measure? Well, we introduce, as usual, this critical density and rescale all three components of the density, the energy density of dust, of radiation, and this fictitious density, or this density of dark energy, by dividing them by this critical density, defining the density parameters omega. And this critical density can be computed because we know the Hubble constant today. This is the Hubble constant in inverse seconds, because I know we discussed that the Hubble time, T Hubble, which is H0 inverse, is measured to be about 13.8 billion years. And using that, I convert to seconds, and this is the Hubble constant in inverse seconds. Everything else here are terms you know. You plug that in, you find that this is the critical density of our universe today. And in terms of this, we rewrite these two equations. Friedmann's energy equation becomes simply h of t squared times everything on the right-hand side after you factor out this critical piece becomes 1 minus omega is a negative k times r0 c squared. And the acceleration equation becomes, again, factoring out h squared, q is just a half of the density of dust, a half because this 8 and this 4 lead to a factor of 1/2. In radiation, the fact that these two terms are equal lead to omega r, and then for the cosmological term, you get the pressure contributing of the opposite sign, so minus omega lambda. So here are our nice rescaled equations. Before we go on to understanding how to solve them, I want to make 2 points that perhaps were not made clearly enough last week, and some of them came up on the forums, and if nothing else, I want to clear up these two misunderstandings. One is the question that sometimes crops up: where did the Big Bang happen? The answer is that the Big Bang happened everywhere. The Big Bang is not an event. It's not a position in space at a particular time. It is a time. What we say if the Big Bang is the time at which the scale factor was 0 or very, very small, we will delve into the beginnings of the universe more this week, then in a homogeneous universe, the scale factor was 0. Densities were very large everywhere. So the Big Bang happened here and the Big Bang happened there. The distance between here and there, no matter where here and there are, was many, many, many orders of magnitude smaller than that it is now. But here was here and there was there. In our co-moving coordinates of this, in which this plot from last week was produced, this is particularly clear. Galaxies, remember, move along these vertical lines, and the Big Bang happened where this galaxy is as much as it happened where this galaxy is, although the distance between these 2 points in space was very small. If, as we will usually assume, the universe is infinite, then when all distances were a factor of 10 to the 18 smaller, it was still infinite. It was just a factor of 10 to the 18 cubed denser, if you're talking about the density of dust. But infinity times 10 to the minus 18 cubed is still infinity. If there is an infinite universe with no edge, its density might have been much larger, but it was just as infinite then as it is now. And so the question of how far are we from the Big Bang is a meaningless question. We are any distance from the Big Bang because it happened everywhere. It is true, of course, that when we look out and we see the cosmic microwave background emitted 380,000 years after the Big Bang, so as close to the Big Bang as we can see, we observe the surface of last scattering 40-some billion light years away. This is not because there is a surface 40-some billion light years away where light last scattered. What it is light last scattered everywhere, including here. But the light that last scattered here has been moving away from here, and we can't see it anymore. It's now 40-odd billion light years away. Whereas the light that was emitted 40-odd billion light years away is just arriving here. The light that was closer has passed us by. The light emitted more at larger distances has not gotten here yet. Some of it never will. But the surface of last scattering is an observational fact. It is not actually a real surface in space. Last scattering, like everything else in a homogeneous universe, happened everywhere. Another version of this is you often see people trying to describe the early universe, and they talk about the entire universe being compressed to the size of a nucleus with unimaginably high values of density and temperature. this is clearly nonsense. If the universe is infinite now, it was infinite then. It was never a tiny dense marble. That tiny dense marble is the way the universe would look from the point of view of someone outside the universe. In particular, that marble has an edge. Our universe, as far as we know, and certainly if it's homogeneous, has no edge. So what one can correctly say is that everything that we observe today, this entire ball with a radius of 46 billion light years that stretches from one side of the surface of last scattering to the other, that was all compressed at some point in the dim, distant past, well, not so dim, but in the distant past, to something the size of a nucleus. What was outside that little marble the size of a nucleus? Well, whatever is now beyond the farthest things we can see. And all indications, as we will discuss, since what we see is homogeneous, there's no reason to imagine that the surface of last scattering of our current present time is some magical place. One reasonably assumes that beyond it lies more of the same, and therefore that tiny, very dense marble was surrounded by equally dense, more stuff, and if the universe is infinite now, it was infinite then. Done with the soapbox. Back to our equations. What is it that we need to do? Well, we have our two equations, and I have noted that to evaluate the parameters, what we are going to do to understand the universe, it is sufficient since we know the time evolution of the density parameters because of the way that densities are governed by energy conservation as the universe expands. It is sufficient to measure parameters of the current era, which is good. That's all we can, in some sense, measure. And so, if we were able to measure, for example, the Hubble constant and the total energy density, so omega, remember, is omega dust plus omega radiation plus omega cosmological term. If you were able to measure that combination today and the Hubble constant, we could determine the curvature of space. On the other hand, if we had those same quantities today and we made this combination, we would be able to predict the deceleration parameter and vice versa. So now what I claimed last week is that we know. I gave you the values for these parameters, but I didn't quite explain how we know them. So the first chore this week is going to be actual real astronomy. We're going to describe how all this theoretical mumbo-jumbo is actually related to experimental evidence and how we can make measurements now and have and are that determine these parameters and are the reason why I say we know so much about the history of the universe. Then, remember, we had this situation where we see a bunch of gravitating matter expanding outward. And the question was, why is it expanding outward? And the answer was, well, it's expanding outward because that's the way it started and it's now moving under the influence of the equations of motion. You have some initial conditions. Can we say something about who threw that rubber ball in the air? It is going to be very tempting to see how far into the past, how close to that actual singularity of the Big Bang we can go and how much our understanding of physics can teach us about early days, and that will be the topic of the second part of this week. And in particular, what is it that we even now, with all our new wisdom, do not know about the universe? And we will raise a whole host of open questions. A word of warning, it's been, as a matter of pedagogical philosophy in this class, our habit to always throw away the details and work with circular orbits and algebraic equations using conservation laws to get as far as we can. And we've gotten quite a bit of insight, I should say, just out of that, or at least that's my opinion. The reason we were able to do that is because we have a very deep understanding, a very thorough understanding of the theory of Keplerian orbits, say. And when you have a very thorough understanding of the physics, it is just a matter of some work to extract an example that has none of the complications of the details, but all of the essence of the physics. As we move through this week, we are gradually moving into territory where the understanding of the physics, certainly by me and in some cases by the community, is incomplete, and therefore it will be harder and harder to extract that simple example, and in some cases we will just have to confront the complexity and report on what the results are of the people who actually work with it. I hope you'll accept this as the best we can do. Hopefully, some way future iteration when one of you is teaching this class, the material for this week will be reducible to simple algebraic spherical Cal examples, indicating that we actually understood it. For now, this is what we have.